My dear friends, welcome back to B Spice. In this session, we'll focus on PID controller. Basically, a simple configuration of PID loop using a Yokogawa DCS system. Okay, friends. In fact, I thought of giving you, concept on how to write a control narrative. In fact, that is under progress. But suddenly I thought, okay, before going to the control narrative, then why don't we, start off with, some concepts related to all the controls like PID, cascade, feed forward, with a typical example, so that you'll have a better idea before going to how to write a control narrative. Okay, so that is the intent. PID controller is names after like a proportional integral derivative control action. In fact, experienced engineers know this. This is mainly targeted at, the freshers and intermediates. Okay. So the PID controller used in vast majority of automatic process control application. Okay. PID controller generally responsible for what? Regulating flow, temperature, pressure level, and host of other industrial process variables. So in this, what I'm going to focus is application of the PID controller. Even though the experienced engineers knows this, this will be a recap, and mainly the focus is more on the freshers, so that you know like PID controller, what is their application, all these. Then second is the controller structure. See what is the look and feel. We call it as a PID, right? So what is inside? How the structure? So that is the one, and also a bit of configuration. That is the main intention of this video. Configuration of the PID loop using Yokogawa DCS system, and also inside the PID, how the parameters are there, the look and feel of the parameters, meaning what are all the parameters inside the PID loop. We need to tune, right? Yeah. So that is the intent of this session. So in olden days, we have been doing this, the manual control like this. See, without automatic controllers, all regulation will have to be done manually, right? Here, what is the gentleman is doing to keep the temperature of water discharged from the industrial gas-fired heater, an operator has to, watch this temperature gauge and adjust the gas control valve accordingly. So that was the process we followed in olden days. So if the water becomes too high, the operator has to close the gas control valve to bring the temperature back to the desired value. Okay, friends? So that is the thing. Okay. So if the water becomes too cold, then he has to open the valve again. So that is the thing. So this is just a typical example. Then comes the automatic control. To relieve our operator from the tedious task of manual control, we automate the controls by installing the PID controller. Okay, typical PID controller. Okay, so the controller has a set point. Okay, they have a set point that the operator can adjust to the desired temperature using this measurement. Okay, so we also have to automate the control valve by installing an actuator positioner so that the controller output, okay, you can see, can change the valve position, and finally provide the controller an indication, okay, an indication of temperature or process variable by installing the temperature transmitter, right? So it takes this input and it gives a control output to control this valve. This is very simple, right? Yes. Okay. Now, the proportional control mode changes the controller output in proportion to the error. This is a proportional control, a P control. So in this, what is happening? The proportional control mode changes the controller output in proportion to the error. So that is the point. See, if error rises, controller output rises, right? Okay, this is the point. If error rises, controller output rises. And if error falls, controller output falls. This is a typo error, controller output falls, and vice versa. So this is how it works. Okay. But if the error is constant, point to take note, friends. If error is constant, controller output is also constant. So that is a point. See, the proportional control, okay, changes the controller output in proportion to the error. Okay. That is the main pointer. Okay. If error rises, controller output rises. Error falls, controller output also falls. And if error is constant, controller output is also constant. So that is a pointer. Okay. Here some terminologies also we are going to learn. Controller gain. There is a terminology called controller gain, KP. Okay. This is also referred to as PID controller, P setting or proportional setting. This is used to change the response time of the controller. This you remember, friends, controller gain KP. Okay. Is called as a P setting, proportional setting. This is used to change the response time of the controller. Okay. So controller action is proportional to the controller gain error. So that is the point. Okay. Right. Higher the controller gain will increase the amount of output action. Okay. So larger will be the error. Obvious, right? Higher the controller gain will increase the amount of output action and larger will be the error. Okay. So the point now note to here is proportional control alone, meaning with this control alone, this has a large drawback. What is that? Offset. Very simple. Okay. Right. So offset is a sustained error that cannot be eliminated by the proportional control alone. So that is the point. Okay. Now what we have to do? Let's see. Let's consider an example of controlling the water level in the tank with a proportional control only. This is a typical proportional control, level control. Okay, friends. As long as the flow out of the tank remains constant, flow out of the tank remains constant, the level, okay, this level will also remains at its set point, right? Understand? Okay. Although controllers are used, controller gain, we discussed right in the last slide, right? Previous slide, controller gain, KP as proportional setting. Some controller use proportional band, PB, that is expressed in percentage. So this is one of the same actually, controller gain, PB, okay? So that is what here, you can see the controller gain KP, 0.1, 0.2, 0.3, all this, and the proportional band. So 0.1 KP means proportional band 1000. So accordingly, you have to do like that. Okay, right. So what is the relationship? Basically, PB, proportional band is equal to 100% by KP. That's it. Okay, just remember this. Right. Now we have a proportional control. Okay, now we will see a bit of an example here. If the operator increases, see here, we discussed that if the flow out of the tank remains constant, then the process variable also remains constant, right? The level remains constant. But here, operator increases the outflow of the tank level will be decrease, right? Will decrease, right? Yes, due to them, why imbalance between the inflow and the outflow. Okay, got it. So when the level decreases, the error increases, right? And our proportional controller increases the controller output to this error. So that is the problem. Okay. When the tank level decreases, error increases, and our proportional control increases the control output proportional to this error. Okay. Consequently, the valve controlling the flow into the tank opens wider. Okay. The valve controls the flow into the tank opens wider and more water flows into the tank, right? So as the level continues to decrease, the valve continues to open until it gets to a point where the inflow matches the outflow. Okay, right. So you can see here at this point here, as the level continues to decrease, valve continues to open until it gets to a point where inflow matches the outflow. So at this point, the tank level remains constant and also the error. You can see here, this is the typical P controller. This is your controller output and this is your PV. You can see here, the error remains constant. That's the point here. Okay. So meaning we cannot nullify the error. Right. Now you see here, as the error remains constant, our proportional control will keep its output constant and the valve also hold its position. The system now remains at balance with the tank level remain below its set point and this called the residual error. It's called the offset. Okay. The system now remains at balance within the tank level, remain below its set point. So it will not reach the set point. Okay. And this residual error is called the offset. So the point is If the controller gain is smaller, system response are slower. That is the point, friend. If the controller gain is smaller, system response also slower and offset is larger. If the controller gain is large, system response is faster and offset is smaller. Got it right? Yes. This one you remember, friends. Okay. So with a proportional controller, the offset will remain until the operator manually applies a bias to the controller's output. What for? To remove the offset. Okay. So it is said that operator has to manually reset the controller, or we can add integral action to the controller. Okay, friends. I hope the proportional control is clear. Okay. Now we go to the integral control. The concept of manual reset as described in proportional controller led to the development of automatic reset, or we call it as a integral control. Okay. So the integral control mode of the controller produces a long-term corrective change in the controller output. What for? To drive the constant error or offset to zero. That is the pointer. See, you can see here the integral action. Okay, this is the integral action. This is the time. So it appears as a ramp, a ramp of which the slope is determined by the size of the error. Okay, controller gain and the main, the integral time is called the I setting of the controller. There we saw P setting, right? Here I setting. You can see here, this is the TA, integral time. Okay, let's move on further. Okay, now you can see here another some concept about integral. See, most controller use integral time in minutes actually. Okay, you can see here minutes, right? 0.05, all these as the unit for integral control, but some use in seconds also. So that proportion also I have given. Okay. Additionally, this integral gain actually, it repeats per minute and repeats per second. Okay. So integral control mode eliminates the offset or the constant error produced in the proportional control mode. So this is the pointer. So in proportional mode, we have the error. But this gentleman, this integral controller eliminates the offset, okay, or the constant error produced in the proportional mode. This is just for your info, friends, okay? Right. So now you can see a same level control, okay? But this time with the PI controller, you can see here, it's trying to, reduce this, nullify this error, right? Okay, maybe I'll go back a little bit behind. You can see here how much is the error here, right, friends? Right. Okay. Now you can see the error is offset is, trying to reduce, right? Yes. So PI controller, P and integral controller simply adds the controller output of P and I modes of the controller. So the integral action rises the controller output, what it does to bring the level back to the set point, thus eliminating the offset associated with the P controller. So this is the integral. So always say proportional, you have offset. Integral, it is trying to eliminate the offset, reduce the offset, okay, as much as possible. Okay, friends, right? So that is the concept here. Now we have a derivative actually. See, the third action is a derivative. Okay, as you can see here, see, basically this is rarely used in controller. Okay, so the system response is highest actually. It's very sensitive to the measurement noise and it makes it very tuning difficult, and the trial methods are applied. Nevertheless, derivative action can make a control loop respond faster. So that is the point. If you want a faster response, go for a derivative, okay? And with less overshoot from the desired set point. Okay, right. So the derivative control mode produces an output based on the rate of change of error. So this is a very important point, rate of change of error. Okay. Derivative action is sometimes called rate as its action is depending on the rate of change of the error. Okay, right, friends. This is the typical derivative action. You can see here. Yes. Increasing time. This is the TD, derivative action. So to have few more understanding on this, these are all just formula which probably the freshers studied there. So derivative control has an adjustable setting called derivative time. This is the one TD, which is the D setting, okay, of the controller. Like P setting, I setting, this is the D setting, okay. Here two units are used for derivative setting. One is the minutes and other is the second. So PID control does provide more control action sooner. That's a faster than possible with P or PI control. So that is the point. Always think, friends, if it is derivative means you will have a faster action. Okay. So if you remember, if you go back, proportional control, you have offset. So the integral control, you nullify the offset, right? And if in derivative, it's a bit faster. Okay. But it has its own disadvantage also. I'll explain here. Okay. Now let's compare the initial controller response of PID and PI. Okay. So the derivative control reduces the time it takes for the level to return its set point. With the derivative control, the challenge is the controller output appears noisier, which is due to the derivative control but sensitivity to the measurement noise. You can see here, this is your PI controller, right? Yes. You can see here, this is the PID. There's a lot of noise, right? Yes. That is the point here. Okay, friends? You got it right? Yes. You can see here a typical. This is your control variable. This is your time. And you can see here, this is uncontrolled. Okay, uncontrolled. Then you have this proportional control. You can see here, this is your proportional control. And you can see here, this is your integral. It reduces the offset, right? Proportional, so much of offset. And the integral, the offset is, reduced, right? Yes, that is the thing. Okay. Then you have this proportional plus integral. You can see here, this is the one, proportional to integral. How good is this? Trying to, with the set point, right? So this is how, the derivative PID works, friends. I hope this is clear, right? And on top of this, if you want a faster action, you can use this derivative control. Okay, right. Now, the second part, what is this look and feel? The controller structure, okay? Controller manufacturer integrate the PID modes in three different arrangements or controller structures. One is series, other is idle, and third is a parallel. Okay, just remember, friends. Some controller allow you to choose between the different control structure as a configuration option. Okay, so what is this in series? Okay, you can see here. This is a very popular controller structure and also called classical, real, or interacting structure. You remember this one, series, okay? Series in the sense by name, you can see here, P, okay, I, D, all in series. Okay, good? Okay, so that's it. This is the typical series control structure. So most of the controller tuning rules are based on this controller structure. Okay, then the second one is idle. Okay, what is this idle? You can see here. This is also called as a non-interacting standard or ISA structure. This was popularized with digital control system. Very popular nowadays actually. Okay. If no derivative is used, meaning the TD is zero, the derivative is zero, then the series and ideal controller structures becomes identical. Correct, right? See, this is not there. Then this is almost like a what do you call it? Series one, right? So that is the point here. Okay. So that is about the ideal. Then this is the parallel. Parallel again, you can see here all these PID modes in parallel. Academic textbooks generally use this parallel form of PID controller, but it is also used in some DCS and PLC. This structure is simple to understand but difficult to tune. So that is the challenge. So because the reason is that it has no controller gain, but has a proportional gain. It don't have a controller gain, it has a proportional gain. So tuning should be done by adjusting all the settings simultaneously, but it's challenging actually. It's not turning, it's a tuning typo error. Okay, sorry for that. And what my recommendation is, try to not use this structure, okay, if possible. So we can go with this idle or you can go with this series. Okay, friends. So this is about the look and feel actually. Now we see a typical example of configuration of PID using Yokogawa DCS. Okay, this is our main intention of this session. See, as we know, PID loop is used when process control is required, right? Okay, here what is happening? The PV, the process variable, is compared with the set point. Okay, and the error signal is converted to an output based on the PID value set in the tuning panel. That is the point. Okay. So the output of the controller, the controls the final element to reduce the error. Okay. So that's a bit of concept. Okay. Now, sorry, listen carefully, friends. You can see you go to your project builder. Okay, the project Yokogawa project. Of course, whoever worked in the system, So what you have to do, you have to go here, the FCS. Okay, then you have to see the configuration. Here you go to the configuration. Then you can see the node here, right? See the node, yeah. So in this node, you can see here this one, AI141 16 channel input and AI841 8 channel output. This is AI, this is AO. You can see here, this is AI, this is AO, right? So you have to fill in this labeling. Yeah, you have to fill in this. So go to the node, then you take this, look for this and you configure this tag. Okay. Then after that, you have to go to the function block. Okay. So you go to the function block, then you can look for the control drawing. This is DR001. Then once you click the control drawing, you can find like this, this page, and you have to select the function block. Okay. In this function block, you can see here, this one, now this is your function block. If you click this, your function block will come. Then you have to select all these, see, PID, all these are there, right? On, off, all these there. So you just choose this PID, then you can drop here. Okay. So that is how you have to do it, friends. Okay. This is a typical configuration of just click it, then can drop and connect it. So this is your input, this is your output. You got it? I hope it's clear. I'll just explain one more time. You go to the project FCS, then you go to the node, particular node, whichever is node 1 or node 2. In this case, node 2. You can see here the AI input, and this is the AO output, analog output. Then you configure your label. That's it, right? Then you have to go to the function block and go to the control drawing. Then click this. Then when you click, the function block will come up. Then you select the PID. Then you drag and drop it. Then you connect it. Okay, that's it, friends. Now, what is inside? This is a typical. This is another typical actually. LT51. Okay, this is a typical LT level transmitter. There is connector to the PID block LC51. You can see here this mode. Mode. All these high, low, low. Velocity limiter, set value high, set value low, all these are PID. You can see here P is 100, I is 20, D is 0, right? All these are this dB, all these there, right? Terminologies all there actually. Okay, that's it, friends. So this is the typical example of a PID configuration. Okay. So if you want any more questions, anything more than this, you can let me know. I'm willing to support you. So the conclusion is, with its proportional integral derivative mode, the PID controller is the most popular method of control by great margin. So if properly tuned, 3 control modes complement each other in the control effort. So the method of tuning must be adjusted to suit the controller's functional characteristics. That's it, friends. Thank you for your time. I hope you like this video. If you like this video, you can show your support by pressing the thumbs up button, and if possible, subscribe and share with your friends. Okay, thank you, and see you soon in the next video. Okay, next in the sense we'll continue with the controllers and maybe the other controls we can take feed forward, cascade, all these. Okay, see you. Bye bye.